Hi, my name is Andrew Sanford. This semester, I spent time reading this book, Five Golden Rules Great Theories of 20th Century Mathematics by John Castee. It has a few chapters, and the one I spent time studying specifically was uh, chapter 4, the Halting Theorem. So it's a theory of computation, and it covers Turing's halting theorem. And really, I was trying to get a better understanding of what are the mathematical theories that underpin our current, basically our modern world and our major. Um, so Turing's halting theorem is basically the same as Gödel's theorem. Um, and what that is it says that the formal definition of it is that for every consistent formalization of arithmetic, there exist arithmetic truths that are not provable within that formal system. So, what this is saying is, um, so a formalization of arithmetic is an algorithm. Um, and so, what it's saying is that there are algorithms that can't prove things. So, in other words, algorithms can't solve every single problem or situation that we face. And so, in that same sense, by extension, that means that computers are unable to solve every problem that we encounter. They can solve many problems, things that can be formalized into a step by step process, and some of those processes are extremely complicated, but they can't solve every problem. Or, in other words, computers can't help us know every truth. And there are two examples of this. The first one is Liar's paradox, and the second one that relates to known numbers. So in Liar's paradox, down here we have two sentences. We'll focus first on this one, which states that this sentence is false. Now, if we assume that the sentence is true, then we have a contradiction there, because this sentence is saying the statement is that this sentence is false. Therefore, because the sentence is true, it means that it's false. And a mathematical algorithm can't come to that conclusion. Now, conversely, if we also believe that the sentence is false, then that means that the sentence itself this whole sentence has to be true. Otherwise, it just doesn't work. And so it's a sort of a paradox. The same thing applies to this statement. Now, the other example with known numbers is that basically there are more numbers in the universe that exist than we know of. So let's say you just get out into kindergarten and the only numbers you know are 1 through 10. Now, of course, as you now know, there are tons of different numbers. There are negative numbers, there are hundreds, there are decimals, and there are even imaginary numbers. So, but to you, you only know this. Now, a computer, we could load into it all known numbers that we're aware of. However, we can take, one. Let's say that in the universe, and anyways, we can take the number 1 and we could subtract 0.1 from it and we'd get 0.9. Well, now we know that number, but you can do so many mathematical variations on this. You could subtract it, factorialize it, a lot of different things. So basically what Gödel's theorem states is that computers can't solve every problem. They can't know everything, and that there are limitations to algorithms. What this means for me, and there's some other research that I think MIT recently talked about, one of their articles, is that I don't think artificial intelligence will ever be able to fully automate humans, because there are some things that as humans we can comprehend and know, but that the underlying mathematical theorems Like, just there aren't mathematical theorems that exist that can solve every problem. And unless we can figure out mathematical theorems to solve some of these issues, like the liar's paradox, or figuring out known numbers, which I would argue, at least with known numbers, can't ever be mathematically solved, um, I think we'll see limitations in what AI can do. So that's what I spent several hours learning about this semester, and that ends this video.